Today, we are diving into the science of fuel, the energy that powers pretty much everything in our world. Have you ever really stopped to think about what's happening inside your car's engine? Or what's actually going on when you fire up the grill for a barbecue? The answer, well, it's both simpler and way more complex than you might think. And it all boils down to one thing: fuels. Yeah? Sounds pretty straightforward, right? You put fuel in, you get energy out. Simple. But the science behind it? Oh, it is absolutely fascinating, and that's exactly what we're going to break down. So buckle up. For the next 5 minutes, we're taking a super fast tour of fuel science. We're going to unlock the core concepts that literally make our world go round. All right, first things first, what is a fuel, really? Let's get right down to the basics of energy. At its heart, a fuel is just any substance that can release useful energy in a controlled way. You can almost think of it like a chemical battery, just sitting there, waiting for us to tap into its stored power. And that energy really comes from two big families. On one hand, you've got your chemical fuels, things like wood, coal, and gasoline, that release energy by burning. That's called combustion. On the other hand, you have nuclear fuels, like uranium, which unleash enormous power by splitting atoms. Now, for today, we're going to stick with that first family, the chemical fuels. Okay, so with all these different energy sources out there, how do scientists keep them all organized? Well, it helps to think of it kind of like a family tree. And it's based on two really simple questions. The first question is, where did it come from? If we can find it in nature and use it pretty much as is, like raw petroleum or a lump of coal, we call that a primary fuel. But if we take that primary fuel and we process it to create something new, like when we refine crude oil into kerosene, then it becomes a secondary or a derived fuel. In the second question, even easier. What's its physical form? Is it a solid, like coal? Is it a liquid, like diesel? Or is it a gas, like the natural gas that might heat your home? This basic sorting is actually super important for understanding how different fuels are stored, moved, and used. So, it's pretty clear that not all fuels are created equal. So how do we measure their energy punch? Well, that brings us to the single most important number for any fuel. It's something called the calorific value. And put simply, it's just a measurement of the total amount of heat a fuel gives off when you burn it completely. Think of it like a fuel's official energy rating. The bigger the number, the more power it's packing. But it's not quite that simple. We actually have two different measurements here: gross and net. Imagine who could capture every single bit of heat from a fire, including the heat that's in the steam it creates. That total amount is the gross value. But in the real world, that steam usually escapes, and it takes energy with it. The heat you're actually left with to do useful work, that's the net value. And that's the number that really matters. Okay, so we can classify fuels, we can measure their energy, but what makes a fuel good? Beyond just raw power. Let's take a look at the ideal fuels report card. First up is performance. Of course, you want a high calorific value, more bang for your buck, but you also want a moderate speed of combustion. See, if it burns too slowly, you just lose heat over time. But if it burns too fast, it becomes uncontrollable, more like an explosion than a useful fire. Next on the list, safety and usability. An ideal fuel has a moderate ignition temperature, so it's not so low that it's a constant fire hazard, but not so high that it's a real pain to get it lit. It also has to be easy to store and transport safely. And this is critical. The burning has to be controllable, meaning you can start it and stop it whenever you want. And finally, you've got efficiency and cost. Any water in a fuel is just wasted energy. You have to boil it away first. You also want very little of what's called non-combustible matter. That's the useless ash that gets left behind. And, of course, the best fuel in the world isn't any good if you can't get it easily and cheaply. So with that ideal checklist in our heads, let's put our 3 types of fuel to the test. It's time for a head-to-head showdown: solid versus liquid versus gas. And this table really lays out the trade-offs perfectly. Look, gaseous fuels, they win on power and efficiency, and they leave no messy ash. But the big downside, storing them is tough and risky. On the complete other end of the spectrum, solid fuels are easy to store, but they're not very efficient and they're hard to control. And as you can see, liquid fuels often hit that practical sweet spot, right there in the middle. This chart really drives that point home.
See that staircase effect? That shows you exactly why something like natural gas is so great for power plants, while solid fuels like coal lose a lot more of their energy as wasted heat. It's a perfect visual of that efficiency trade-off we were just talking about.
But measuring a fuel isn't just about how much heat it can make. We have to zoom out and look at the bigger picture. We have to think about what happens after the burn. Because the story doesn't just stop with energy. Every single real-world fuel, when it burns, leaves something else behind. Unlike our perfect ideal fuel, they release byproducts like carbon dioxide and sulfur dioxide, the pollutants that have a huge impact on our environment. And that really brings us to our final thought. We've just spent a few minutes breaking down the science of what makes a fuel good. Powerful, efficient, safe. But the much, much bigger question that we're left with is this: what makes a fuel right for our future? Now that is something to think about.